Welcome to this webinar with the name Enabling HPC, which means High Performance Computation, and AI for Traffic Modeling. I'm Radim Cmar, the EVEREST project manager, which is responsible for the application use case traffic modeling for smart cities. And I would like to present our ecosystem. What are its challenges? What are the critical parts which needs to be taken care of? And I would like to demonstrate also the methodology of translating this ecosystem or this application into a more performant one. And this is through the use of technology which is being developed within the EVEREST project by our technological partners. Few mentions about the EVEREST. EVEREST stands for Design Environment for Extreme Scale Big Data and Analytics on Heterogeneous Platforms. In other words, it's a design environment that simplifies the programmability of high-performance big data-oriented applications, such as this traffic modeling ecosystem, which comprises of several challenging computational kernels which are revolving around machine learning algorithms and big data management, with large amounts of data going up to terabytes. The focus of EVEREST is on applications which exhibit heterogeneity, which require reconfigurability or a distributed approach, which requires scalability and security. Traffic modeling use case brought by Sygic is one of the three demonstrators which is being demonstrated within the EVEREST project. There is a Duferco project partner which demonstrates renewable energy prediction, where the weather prediction is first used, which affects the generation of energy from wind turbines. There is another use case brought by Numtech partner, which demonstrates air quality monitoring and prediction as well. Both these use cases rely on weather forecast model, which is provided and managed and optimized by Cmar partner. As you might expect, all these use cases are about learning patterns from a huge amount of measurement data while applying artificial intelligence algorithms. The outline of this webinar is the following. First, I will introduce the traffic modeling ecosystem for smart mobility in terms of its function design. Second, I will describe the traffic modeling architecture, what data are involved in this ecosystem, what is the computation required in this ecosystem. Third, I will go over the goals and challenges with the application of EVEREST tooling. Means what are the objectives, where we expect help from our partners, what is the outcome to be considered as success. And finally, I will wrap up with drawing some conclusions. So why is traffic modeling important for cities? It's because there is 70% of population lives in cities, and this figure is still on the rise. So we cannot expect that the traffic problems which we have now will diminish in the future. Probably this problem will become even more exposed. City congestion costs money. It's evaluated as 1% of GDP, and even worse, it accounts for the tons of emissions, and particularly traffic takes 40% of all CO2 emissions. And the congestions are, of course, the major contributors to the situation. So the goal of the city is really to diminish the congestion, and this is what the traffic modeling helps with. So if city wants to improve the traffic, it needs to know, it needs to have a good analytics of the road infrastructure and also the prediction tooling. And what we see is many cities are still not using traffic analytics tooling because the products on the market are either complicated to use, which require very expert knowledge and takes long to calculate and leave the data provisioning and entry to analysts, and the data are sometimes really problematic to obtain. So our goal is to provide a traffic ecosystem which allows complex analysis of the mobility across the city on all the roads, so the roads characterization in terms of macroscopic fundamental diagram. And this is also with securing the data input, automatic channels, streaming data from navigation devices like, for example, from Sygic. Our product contains the computation of traffic profiles over the week periods, contains the traffic analysis tool, for example, with hypothetical scenarios when there is a closure or when there is a change in traffic infrastructure. And then it provides also two services for which is the traffic prediction per each road segment and routing service with some collaborative intelligence, which could be interesting for cities to use, which helps to distribute the traffic to be more balanced in terms of the load of the road network. And there are technological challenges and required optimizations with our solutions. So as it works with the big data, the major big data are the floating car data, which are the data collected from vehicles. I will describe later. And these are in terms of gigabytes daily. And there are also the computations necessary for this traffic modeling to be providing good value. And so the computations, besides others, just to name few, are convolution neural networks, Bayesian inference, or hidden Markov model, or probabilistic routing. Let me look at the traffic modeling use case from the high-level architecture point of view. So our traffic computation ecosystem consists of several computationally intensive elements. These are the map matching processor, traffic simulator, traffic prediction model training, and there are two services, traffic prediction service and intelligent routing. All these elements are computationally intensive and require special attention, especially with respect to optimization. There are three major input data to the system. First one, so-called floating car data, or FCD. These data is provided by Sygic from the users who are using Sygic mobile navigation. Sygic has approximately 5 million monthly active users across Europe, and each of these users is potential contributor to these data. So one data record represents the GPS position and the speed of a vehicle at a particular time instance. And these data are collected from users on average in interval of 30 seconds, Of course, these data are anonymous and only collected from the users who agree with that. Another major input to the system is so-called origin destination matrix, ODM. So these are the data which typically gather the mobile operators, and they give information about the global mobility of the citizens across the city. So the city is organized in terms of cells, which are approximately 500 meters times 500 meter, and this data represents the mobility between cells of the user. So one record of the matrix, for example, defines that from a certain cell, from the cell A to the cell B at a particular time instance or window, there are like 500 people moving. And then the third data is the road network, or it's map information, which is provided by Sygic. The output of the system is the speed profiles. This is the information which for each road or for each major road defines the speed information, statistical speed information across the whole day for a particular day within a week. This is the information which is used for statistical prediction, and it's already an information interesting for traffic managers and analysts, but what our ecosystem offers is more advanced output, which we call 3D traffic model. So this means that we will not only produce or we calculate the speed information on a road, but also the information about the density and also the flow or intensity, meaning how many vehicle passes a certain road per second or per minute. And so this information is already more valuable we believe more valuable to the traffic managers, traffic analysts and planners, because they can better see the characterization of their road network. And then we also expose two services, traffic prediction and intelligent routing. So these are the REST API services for mobile navigations, so which is used by Sygic but could be used for another navigation applications. And so what's maybe interesting is this system through the traffic simulator generates the whole data which traffic simulator generates. It means that there are also the hypothetical scenarios, but also the scenarios which are reflecting the reality calibrated through the data which are delivered to the system. So these data, produced by traffic simulator, are considered as training data, which can train the prediction models. For example, knowing the traffic prediction on major roads for forthcoming 1 hour or 2 hours. Let me show you the more detailed architecture view on computation, on our computation use case. It starts from importing the data, big data input from Sygic backend, and ends with providing the services by mobile applications. And also it shows the intermediate results as were already described as a 3D model or a speed profile model, which is the output used or meant for traffic analysts. So as you see, the system is split into 4 big computational components like FCD data processing, traffic simulator, model training, and prediction and routing. Each of these components have a well-defined interface, and according to EVEREST methodology, they form a workflow which is optimized as a whole. Each workflow typically contains one or more kernels which has been identified as critical components which are subject to optimization and acceleration. So, for example, the FCD data processing contains the map matching algorithm within which there are kernels such as Viterbi or Dijkstra routing algorithm which we need to accelerate. For the traffic simulator, there is the probabilistic time-dependent routing kernel which is subject to optimization. For model training, we optimize the neural networks which are contained inside. And for traffic prediction and routing services, there are the inference of the neural network prediction and also the time-dependent routing, a different version which is contained within this service. So let me dive deeper into the details of our architecture. So let's have a look at the workflow FCD data processing. So input to the workflow are the floating car data and the road network, and the output is to calculate the speed profiles with the map matching processor. The processing is about the daily streaming of floating car data from external systems such as Sygic backend, and it is really in the extent of gigabytes a day. And this is something which this is the mechanisms through which we want to collect for several days in a row. What it contains inside is, of course, there needs to be out of the whole big data, the consecutive trajectories needs to be filtered out, and these are map matched with the hidden Markov model algorithm, which contains Viterbi and Dijkstra components. And as a result, these roads are the road speeds, which needs to be partitioned into georectangles for more comfortable processing of subsequent components. So the output is the road speed profiles. As you see, the red color represents the congestion, and the green represents free flow. So as you see, the congestion is typically around 8 o'clock in the morning and 4 o'clock in 4 p.m. So what optimization needed here is the big data management and accessing, and kernel acceleration, and it's with EVEREST SDK tooling. So the kernel acceleration of Viterbi and Dijkstra. Current performance without optimization on standard cloud systems which we have takes like 1 day of data of approximately, which is approximately 20 million samples. This execution time takes something more than 4 hours, and to satisfy our goals for the kind of overnight update of the model, we specify the acceleration of at least 3x for such processing. We envision technology from EVEREST, which is the kernel mapping from C++, how the code is described, to FPGA. As you can see here, is depicted few results of like 9 roads of the system, which shows the road speed calculated by the system from the data, from the very imprecise, noisy data, and then with some red curve representing the approximation. So as you see, it really again fits the assumption that there are low speeds at around the peak hours. Let me continue with showing things deeper here with the workflow, with the next workflow, which is the traffic simulator. This traffic simulator takes in as an input origin destination matrix data and the road speed profiles, and generates the 3D model as well as the training sequence for prediction algorithms. The road speed data and origin destination matrix are given for a particular date, which we want to do the calculation. This simulator is executing in 15 minutes intervals. What for the optimization we need here is the scheduling of the node tasks. This is with the EVEREST tooling, as well as the kernel acceleration of the probabilistic time-dependent routing. Currently, our baseline performance for the simulation for this time range from 5 to 21 on the Prague city with 50,000 vehicles, we have the execution time approximately 33 hours. We stipulated here the speed up required to satisfy our overall objectives as 5 times acceleration. Here we envision the technology to be used is again the kernel mapping towards the FPGA here from the Rust source code, and also we want to use the optimization of the HyperQ tooling. Here I demonstrate the output of the 3D model on 4 different roads. Where you can see there is this function that with a higher speed, with a higher density, that the speed of course drops, and there is this special curve characterization, which you might know from the macroscopic fundamental diagram. And as a last but not least workflow, I want to discuss the traffic prediction model training. So this workflow takes as an input training sequence and generates the neural network models for all the crossings or all the roads in the city. So as for the processing, the training data is taken from the traffic simulator. Convolutional neural network is applied now, which is with 4 layers, and prediction model is calculating the prediction for 1 hour ahead based on the real-time input. So what we need to optimize here is big data reading and kernel acceleration of the neural network. Current performance on the Prague city, where we calculated with 10,000 major roads. The execution of the training takes along 7 days on our conventional cloud architecture. So here our objective is really to have a major speed up with the technology from going from Python towards the FPGA. For the execution of our reference design, we will use Lex's environment. which is the output of another Horizon 2020 project. Lexus is the framework which can accommodate heterogeneous system and provide an execution on HPC premises, able to connect to external compute systems. So we will use it to accommodate our 4 workflows, provide data communication between those workflows, and also to execute remote calls to accelerators. So I'm coming to the summary. I introduced the reference design of traffic ecosystem, which was defined by algorithms described in various languages such as C++, Rust, Python, and it is currently executed on common infrastructures with the goal to port it to Lexus to get flexibility on hardware mapping and subsequent optimization. I showed that the traffic ecosystem is defined with components which are becoming EVEREST workflows, while each workflow must have a clear definition of a data interface. Critical kernels must be identified to be subject to optimization, together with, of course, some KPIs. I show that each workflow typically contains 1 or more kernels suitable for optimization. Here we identify components such as Dijkstra, Viterbi, neural network, or probabilistic routing. I also indicated that the execution times of the different components, and as is our goal to have the traffic model update with a daily input data income to have updated overnight, then of course we need some accelerations of those components, and what we identified, we need speed up from 3x up to 10x for different components. And what I want to mention at the end is this EVEREST SDK for kernel optimizations is on the way with the first outputs having the FPGA translation of the kernels from different languages. And here is our consortium. Thank you for your attention.